Hi everyone. So we're going to continue on Module 10. This is going to be a little bit outside the flow of the textbook. The book did cover this in Chapter 7, but that was in the analog part. And now we're going to adopt this for digital. Okay. So as you saw in the last lecture, right, having memory, right, having the ability to remember things is very useful. Hopefully we don't have to prove that. This really opens up a different logical branch of operations that we can do on a circuit. Okay. Remember when we did the adder, the multiplier, the multiplexer, right? Once your input is set, right, the output is always going to be following whatever that logic is, right? So you're adding 1 and 1, right? 1 plus 1 always equals to 0 with a carry of 1, right? That happens in one step, okay? This is known as combinatoric logic. Sorry about that. Okay. And the way I remember this is that, well, combination, right? Combinatoric means combinations. It just combines multiple inputs. Once those inputs are set, the output comes out. Okay. And this really happens at the speed of electrical signal going through your device, right? So if your device, the longest wire you got is 1 foot, that happens in a nanosecond. So it's very fast. However, right, when you want to store information for the next calculation, meaning use your memory, right, to do more complicated things, you have to use this thing called sequential logic. So you have to do step A, remember it, and then use that step A's information for your next step. Okay, so this is how sequential logic comes in. Okay, and why we introduce this now, because right, without memory, you can never do sequential logic because you would never forget, you would never remember what you did in the previous step. Okay. From the construction of the edge trigger flip-flop that we talked about last time, right? Remember that information can only be well, be written. Basically, you can always read it, right? Once per clock cycle. In this case, right, on the positive edge, meaning when the clock goes from low to high, that's when the information goes from D over to Q. And I'm going to see that that's actually not the real case with faster electronics. Okay, so let's just talk about how this clock gets generated inside your device. Okay. Stack already talked about this in section 7.10. So I suggest if you don't remember what that clock is like, go back. It's an analog clock, and we're going to use it digitally, of course. Okay. And this device is basically just an op amp with 3 resistor and a capacitor, and it has no inputs. Okay. And then you have V1 and V1 and V2 as the outputs that you can grab onto with your scope probe. And the behavior of this, I'm going to go through this pretty quickly, right, is that while this is an oscillator where basically what you're doing is you're charging the capacitor and discharging the capacitor, charging the capacitor, discharging the capacitor over and over and over again. Because when the capacitor reaches a certain threshold, it'll discharge. When it reaches another threshold, it'll charge again. And so V2, right here, right, this blue line. Actually, I probably should have just colored it blue, right? There's this blue line here. Okay, so that's the oscillating part. Okay, this operation amplifier, which is actually being used as a comparator, okay, gives you a digital output basically, where you have the whatever VEE and VCC is, and basically, if V minus is bigger than whatever V plus is, it goes to the negative voltage, and whenever V minus is bigger than whenever V minus is smaller than V plus, then it goes to the positive voltage. It basically rails the power supply, right? In this case, okay, the way we use it in digital, if you're using 5 volt TTL, this bottom here is set at 0 volt. The top here is set at 5 volts. Okay, and therefore it follows the same voltage state as our TTL logic. Okay, and of course this can change, right? Because that's only in the case of 5 volt TTL. If your TTL is 3 volts or 1.8, or you're using CMOS or other type of voltage settings for your logic gate family, right? Then you use those instead. Okay. So you can make this right using a function generator, and we're gonna see a little bit of this in the lab to begin with on your breadboard, because we don't want you to have to build a clock in order to test some of these devices, and then your clock may not be working properly, stuff like that. Okay. Right. So this function generator, well, I mean, technically, actually, inside a function generator is a clock, right? And this is how it actually gets generated, and then the output, right, is these square waves that you like. It's called a square wave, but can be used as a clock. Okay, so in 5 volt TTL logic, low means 0 volts, high means 5 volts, so you have 0, 5, 0, 5, 0, 5 up and down like that. Okay, and when you're working on a breadboard, you really don't want to run faster than a few hundred kilohertz. Anything faster than that is really going to cause a problem, because you're going to have pickup, and the breadboard you're going to get a lot of noise. Okay, but in the FPGA, where wires are a lot shorter, right? In fact, a lot of the wiring actually happens inside a single chip, right? We use a 100 megahertz clock, which is the speed that you probably want to run at around with modern day electronics. There are some clocks, some electronics that can run at 200 megahertz, maybe even 400 megahertz, if you do a double data rate. But the limitation on the clock speed, okay, is really due to the fact that light propagates at a finite speed. Okay, 100 megahertz is equivalent to a period of 10 nanoseconds. So 10 nanoseconds means the light can travel about 10 feet. Okay, so if any wire that's longer than 10 feet is going to get out of sync. So if you're, let's say you're building a computer or something like that, inside that computer, there's probably a couple of feet of wiring. So if you're running at anything above 200 megahertz, they'll get out of sync, because you're going to, you can't change that yourself. If the manufacturer try to set that at much higher, let's say I want a 1 gigahertz clock speed computer, you can't do that, because, right, the wiring will just have a propagation delay because of that. Okay, so that's how you actually build a clock in your on a breadboard. If you wanted to, just an op amp and a 3 resistor and a capacitor. In your FPGA, I'm going to show you how you can get a clock. The clock is built in. So in your top file, all you have to do is just add input space clock as one of your inputs. And then, let's say in this code, I'm just make the clock the same as the LED. So it's just going to blink. Okay. And this LED is going to blink at 100 megahertz, right? Because this is a 100 megahertz clock. Right? 100 million times per second. Okay. Since we cannot see 100 megahertz, this is just going to look like a little dim light. In fact, it'll be about half as dim as what you would have if you just switch it on completely, right? Because the light is on half the time, off half the time. Basically, then that'll basically make it about half as bright. But, well, half the number of photons emitted. But I'm not sure how I actually perceive light. I think it's on a log scale also. Okay, so that's not very useful to look at. What we can do is we can slow down this clock, because we can always make a slower clock out of a faster clock. Okay, down here I made a module, and you guys can copy this, but I want you guys to understand how it actually works. Okay, previous lab, I have you guys define a full adder. This is the same type of techniques you're using, where, right, on your Verilog file, right, you have the timing stuff. There's some line about timing, and then you have module, and I always have you guys name things top module or top file, right? And then what's the stuff up here, right? And then you have input, switch, you know, I'm not going to write it all out. You have a bunch of little arguments here. And then you end with a apostrophe here. And then you do your code on here, right? And then you have end module, right? Right. You can make additional modules in the same file or in a different file if you want. So this is actually goes beneath the last end module of your top file. Okay. You can have multiple modules in your file, right? Or you can import from different files also, which is what you did with the hex display, by the way. So you have a bunch of code in here, you have a bunch of code in here, right? And it does different things, okay? So I'm just going to show you how you can pass information back and forth between these two, between the module and your top file, which is the module that gets run first, okay? And 99.99% of the time, Vivado is able to figure out, okay, I want to run this top file first. Once in a while, it does get confused and try to, let's say, run your slow clock first. In that case, the code is not going to compile it. You're not going to be able to synthesize it. Okay, but then you just have to go back and manually set your top file to be the first module that gets run. Okay, if you were developing things, you know, in the order that we do in the lab, it should work out because you always define the top file first, and that's the one it picks. Okay, so that does happen. Just make sure your top file is the first set of code that gets synthesized, and because it's kind of like the mother module, and it calls like other little baby modules around. Okay. All right. So let's see how this works. Okay. So this has defined as module, right? And then I have to give it a name. I'm going to call it slow clock, just spelled out. Okay. No space, right? Is allowed. I think you could put an underscore there if you want, but I just like this, you know, capital S, capital C, you know, you can see that as a slow clock. And you give it two different things. These can be inputs, outputs, or registries. Okay. So this is a output registry. This is just a regular input wire. Okay. Okay. So now inside here, inside this module, all you have access to are these two things. Okay, you can only use those two things that can communicate with the outside world. Okay. All right. So the first thing we found is that we declare a registry of 27 bits, right? 26 to 0 equals 27. And I'm going to call that count. It's not for like the title. It's just a counter. Okay. And I'm going to start it at 0. Okay. And this is going to count. And if you take 2 to the 27th power, you get about 67 million. And this is a counter that I just need to count up to that much, because I'm never going to count above that. Okay. And you will see why in the next little bits of the code. Okay. Since we're dealing with registry, in order to change a registry, you have to be using an edge of a clock. Okay. And that's the edge of the clock in from here, right? You can see that direct connection there. So we're using the positive edge of this clock. So always at the positive edge of clock in, which you would have, you know, which is the input clock. Okay, start doing something. Okay, what am I doing? I'm going to make count, right, be updated to count plus 1. I'm just going to iterate, right? If count is 0, I'm going to make it into 1. And the way I update that information is by using this little non-blocking assignment operator, right? With this less than equal thing. And you think about it as you're basically moving what's on the right into the left. You're moving into that house, okay? All right. So, well, what else do I do? Well, if count is equal to 12,500,000, right? Do something. Like what do I do when that happens, okay? Well, what I do, I make clock 0. Okay, why do I want to reset the clock? Sorry, not clock. I make the count 0. Okay, and then what I do is I make clock out be the opposite of clock out. Okay, It's like, wait, what are you doing? So if a clock out started at 0, right, after this line, what happened is that clock out becomes 1. If clock out is 1, it becomes 0. So you're just toggling clock out, okay? So what is happening is that the clock out gets up and down, right, like this. Okay. Whenever this count reaches about 12,500,000. Why 12,500,000? Because I'm expecting this clock in to be 100 million per second. That's 100 megahertz, right? If you take this and you divide it, because that's how you divide, okay? You get the answer is going to be 8, okay? 12.5 million into 100 million is 8, okay? So what I'm doing is I'm toggling this clock out 8 times per second, okay? But each toggle, right, makes it go up. The second toggle makes it go down. So each cycle is actually 2 toggles, okay? So basically what I have done is I made clock in, I converted a 100 megahertz clock to a 4 hertz clock, okay? And if you program this in and you make the LED blink at 4 hertz, you will see it blink, right? Because our eyes are fast enough to see that. Okay, all right, so as I stated in the full adder module, this is basically a template, right, that you define after your end modules, okay? In order to use it to actually make it real, as opposed to just a blueprint or a template for it, you have to do this, you have to instantiate it in your top file, okay? So to instantiate it, what I'm going to do is I'm going to make, something my clock, okay? Okay, all right? And this is a wire, not a registry, okay? Because I don't want to deal with registry unless I have to, okay? What happened is that this slow clock, right, which is the name of this module, right? I'm going to name it something else. You just cannot use slow clock because that's already used. So I'm going to call it slow clock 1, okay? And then you pass it that 100 megahertz clock, right? This is the 100 megahertz clock that we're passing. And then my clock, right? This is the slow one, that's the 4 hertz one I'm going to get back, okay? Notice that I'm able to pass a wire in there, even though the input is being treated as a registry, okay? The reason you have to treat the input as a registry is that the module has to remember what that state is. Because what happened is that if you don't use a registry, it's literally just it's literally just a non-registry is a hard wire, and therefore it will never update, okay? And then you assign that to be your LED, and then your LED will blink at 4 hertz instead, okay? You can do this logical operations at 200 megahertz, even though you only have a 100 megahertz clock, right? You can do the positive edge and negative edge. You can trigger on both edges, okay? And this is basically the technology of double data rate memory, okay? But be a little careful, right? If you're doing things really fast, remember there is a finite distance that light travels, and that's 1 foot per nanosecond. And electrical signal actually techniques travel even a little bit slower than that, okay? So if you're doing things at clock cycle that are 5 nanoseconds apart, the light can at most travel 5 feet. It's probably going to be less, okay? So don't expect the signal to reach the end of this line if you're doing something really, really fast, okay? So this clock thing gives us a kind of a cool opportunity to do a little bit, teach you thing called simulation and timing diagram. So what I'm going to do is I'm going to pull that up on Vivado, and I'll share that screen. Vivado pops up. Okay, hopefully you guys can see my Vivado. Already made the lab for it. Well, this is going to be lab 10. Hopefully, yeah, this one. Okay, so lab 10. All right, so I made a slow clock module in this using the same Arctic 7 board with the same constraint file. And this is the top file that I have up, right? So, so you can see that this is very similar code than what I show you on OneNote already. This display stuff is not important because we're not going to use it anyway, because we're just going to use the LED. But so this is my slow clock module. Instead of 12.5 million, I set this to 100. This is going to be a much faster clock. So 100 divided by 100 million is 1 million. But remember, this is the toggle, so it's going to toggle the output clock 1,000,000 times per second. So that means it's not a 1 megahertz clock. It's actually a 500,000 or 500,000 hertz clock. Okay. So the reason I reduced this is because if I did the 12 million, you would just see a bar of fast clock and not see the change in the slow clock. So in order to use this tool, you have to run at least the synthesis. Okay. And also, if you want, you can also run the implementation. Actually, I'll probably do both just to make sure that I can also show you the implementation tool, that the tools you can see after you implemented it. So I'll pause while this is happening. Okay. Okay. So my implementation is still running, but I can open the synthesis already because I already synthesized this code. Remember, the synthesization is basically just translating code into circuit diagrams, right? So Vivado should understand how my circuit work, okay? And what I'm doing is I'm going to do the simulation stuff, okay? So instead of programming a real device and see how it works, I can actually see how it works with just a simulation, which is close to reality. I'm going to showcase some of the stuff that it may not show you accurately, okay? So since I only have the synthesis done, I'm going to do the post-synthesis timing simulation, okay? Should be pretty quick to make this. I am running both the implementation and this at the same time, so I'm using a lot of the cores on my laptop, but it does come out, okay? In case you're wondering, this is the physical wiring on your FPGA. So these are mapped at different registries, logic gates, and block RAM mapping. So you can see that, and I'll show you how that works. So the implementation finish, I'm not going to generate the bitstream because I'm not going to program the device with it anyway. Okay, so close that. Okay, so after you get your run simulation, you click on post synthesis timing simulation. You should get a window that looks like this. I'm going to make this a little wider, just a lot of wasted space here. Okay. Okay, so what this is showing is basically the state of the signals as they go up and down. Okay, so we have the states of all the switches, which are Z. The Z means is unknown. I don't know. I mean, Vivado doesn't know what the state of these things are, so we're not using the switches anyway. I probably should have removed this AN and the segment thing. Basically, that's for the hex display. We don't actually need that. Those are also in unknown state. And then the LED is also in unknown state, except for one, right? That's because I programmed LED 0 to be the same state as my clock, my slow clock. Okay, but in order for me to simulate how that behaves, I have to initialize the original fast clock, the 100 megahertz clock. I'm going to move this over here, right? This clock here. Remember, this is a 100 megahertz clock. But right now, right, Vivado say, I don't know what this is. Well, because, right, Vivado doesn't necessarily have access to the hardware that it knows, okay, that, oh, is it a 100 megahertz clock? Is it a 10 megahertz? It could be any speed clock it want, right? So I'm going to program, basically force this to be a 100 megahertz clock. For some reason, my menu is popping up on a different screen. Let's see if I can make it so I can show you what I'm clicking on. It's not doing that. Let's see if I can lower this. Really? Okay. Okay. Anyway, I'm just going to describe what I'm clicking on. Okay, so when you right click this, okay, you can then click on force clock. Okay, and now it's showing you, okay, on this force clock pop-up that you'll see once you right click on CLK and then click on force clock. What I want is I want the edges to be going from 1 to 0, and I want this to be a 100 megahertz clock. So that means the period has to be 10 nanosecond, not 100 nanoseconds. So I'm going to set that and say that okay. And then up on top here, hopefully you can see my mouse. Okay. This will allow you to pick how long you want to run the simulation, or just run it forever if you want. Okay. I'm just going to run it for a millisecond because, right, I'm expecting the LED to blink at 500 times per second. So in 1 millisecond, it should blink 500 times, right? And let's see if that's true. Okay. Okay. Right. So in fact, what I'm going to do is I'm going to move this LED right after this clock. You can actually move these things around. So the signal for the clock is up here. Hopefully I fix that to be a force clock. Oh, why did I not that happen? Okay. Okay. All right, let's do that. Okay. And then I'm going to put the LED's value here. I just kind of dragged it up, so it just made a little copy of it up there. Okay. And then when you push play here for 1 millisecond, you're going to see a bunch of greens and blues. It's like, what is this stuff? Okay. So what I need to do, so you can see that the time scale here is in picoseconds, which is not what we want to look at. So I'm going to zoom out with this minus button a lot. Okay, now I'm starting to see, you see these? See, this is the clock cycles. I'm going to move this down actually, so this is a little confusing. Okay, so you can see that these are 5 nanoseconds width, right? Each of the clock period is 10 nanoseconds, right? That's our 100 megahertz clock. Okay, I'm going to zoom out even more so we can see the LED blinking. So for every 100 of these, the LED goes up and down once, right? Well, goes up once and then goes down once in another 100. So you can see how this code works, right? So every 100 LED of regular clock, if I go back to the project, right? Every time the regular clock goes up 100 times, my clock goes up once. Well, my clock gets toggled once. Okay, so it's actually 200 times that it goes up and down. Okay, let's go back to the timing screen. So, if you want to switch back between, if you just click on the top here, it allows you to go from project to simulation. Okay, you can even chop to synthesis if you want, which shows you this map. We'll talk about that later. Okay, so the other thing we're going to see here is that I'm going to zoom in a little bit more in here in order to see. So you're going to see that, right? There's also this, instead of just clock, I have clock iBuff and I have clock iBuff G. So what are these things? So since these signals are so fast, okay, what the simulation is doing is simulating a delay between the clock itself and the buffer. So these buff means buffer. So these are the buffers that are interconnected. So the real clock happens at some speed, right? But when you actually receive the signal, there's a slight delay between them already. You can actually see this. If I zoom in even more, oops, zoom in too much, right? So the regular clock went high, and then about 1.3 nanoseconds later, that's when the buffer gets it. And this is when you actually have access to it. Okay. And what's the difference in iBuff and iBufferG? I think iBufferG is for external devices. So there's even a longer delay for the for external devices. So this is where if you plug in something to your FPGA, you want to get that output. Okay. So there's like almost a 2 nanosecond delay if you want the iBuffG version of it. Okay. So this is the actual thing that happens inside the FPGA. This is for outside. Okay. Another thing I want to show you is that you can go out here. Let's see, you can zoom in here. Right. Remember, this clock is supposed to toggle on the positive edge of your clock signal. Well, I mean, even if you take the regular clock or just the actual clock that you see from the buffer, you can see that, right, the toggles does not happen at the positive edge, right? And that's because, right, in order for this information to get propagated properly, there are multiple logic gates that you're jumping through, and each of these logic gates will give you a slight delay. Okay. In fact, what you can do is you can actually see this. I'm going to have to run the close implementation simulation, I think, to see this. Okay. And then down here, not synthesis. Yeah, so this report timing summary. Oops. Where'd it go? There it goes. Okay. I'm just going to call it that. You mean it's probably better to name it something else, but I'm just showing you how this works right now. Okay. So you can see that there's a timing report where it's reporting how long does things actually take for it to happen. Okay. So this worst negative slack, meaning there's a delay of 6 nanosecond, up to 6 nanosecond in any of your logic. So if you're counting on things to happen, you know, within 6 nanoseconds, less than 6 nanoseconds, don't count on that to happen. Okay. This is the worst case, right? So so this is where things are. So you want to design around this so that you're not, you know, you're not in this, even in this simple device, you probably don't want to take both the positive and the negative edge, right? And expect those to operate independently of each other, because that's only going to be 5 nanoseconds apart. Okay, so so the reason for that, let's see if I can click on the timing summary. So remember where that is. The output delay, ensure clock path. There should be one where it tells you how many steps it takes, how many logic gates it takes in order to get to where everything needs to get to. Basically, the longest path that you have in order to get to all your logical steps. This clock endpoints. Oh yeah, there it goes. Okay, so this is under intra clock path, sysclock pin setup. All these menus are pretty hidden. So basically, there are 10 different paths that the electrical signal goes through. And basically, what happened is that there are multiple routes that things can pass through. And then there's this fan out, meaning it just splits the signal. And basically, each of these logic gate steps are expected to have 0.6 nanoseconds of delay, and then depending on how many steps it needs in order to get through that, right, it multiplies that and figure out, okay, this is the delay that will happen at, you know, at this point, and of 3.5 nanoseconds because of the logic. And there's also the propagation. The net means the wire, right? And you basically add these together, and I think that's how I figure out the 6.2 nanosecond delay. That's the maximum that we'll get on this particular design. Okay, you can design things to minimize that, to make things go faster and faster and faster, but for our application, just don't do anything less than 10 nanoseconds. And you can run this report and just make sure things actually operate correctly within that 100 megahertz clock that you're using. If you can't, then you have to slow down your clock to make sure the logic actually still flows through without creating errors. Okay, so that's how you play with the both the timing report and also, more importantly, these timing diagrams. And remember that in order for you to see these diagrams, you have to set this clock to something, because right now by default it just gives you nothing because it doesn't know what your clock is. And then once you set that up, you can have it go up and down, and then you can see how your signal goes up and down and what delays are there in these clocks. Okay. All right, so that's all, and hopefully we'll see you start on the pre-lab, and then we'll go through some of these exercises in the pre-lab and the lab. Okay. All right. Thanks.